And even though you can graph these with your calculator, the problem is that you end up with graphs like this, where if we do our standard window again, it's hard to tell what's happening with this because it's going down so far, it's hard to see all of the graph at once. So it's really nice to be able to tell just from what we can see from the function formula to get an idea what's going to happen. And then we can check with our calculator graph and make sure that the two things agree. When we talk about the leading term test, we already talked about how to find the leading coefficient and the degree. The reason that we want to know what those are is that they make a difference in what the graph is going to look like. The first thing we can look at is the leading coefficient. And really the only thing that matters with this is whether it's positive or negative. If the leading coefficient is a positive number, then that's going to tell us that our graph is going to go up as we go towards the right end. That would mean that as we go towards the right end out here, our graph is going to go up like that. It doesn't tell us about what's happening anywhere else on the graph, just as we go towards that end. If our leading coefficient is a negative number, then our graph is going to go down on the right. So in that case, it would be doing something like this. The leading coefficient just tells us what's happening on the right end of the graph. The other thing we got from that leading term was the degree. That's going to tell us something different. This is actually going to tell us what's happening on the left end, if we already know what's happening on the right end. For the degree, we can look at whether it's an even number or an odd number. If it's even, then the graph has the same behavior on the left end that it did on the right end. So if this is true, then the behavior on the left and the right ends is the same. This would be something, this could be two different possibilities. This would mean either going up on both ends, like this, or it could be going down on both ends. If we have an even degree, then it's doing one of these two things. If the degree is odd, then the behavior on the two ends is the opposite. It's the opposite on the left end from what it is on the right end. That means it's either going down on the left and up on the right, or it's going up on the left and down on the right. What this all comes down to, if we put these two things together, is that we're going to have one of these four pictures. And this is what we call our end behavior, because we're just talking about what happens on the left and right ends of the graph. This doesn't tell us what's happening in the middle. That has to do with the x-intercepts and the relative mins and the relative maxes. This is just saying what's happening on the two ends. Got to be one of these four things. And to find this out, we just need to look at the leading coefficient and the degree. If we have this polynomial, this one is in standard form, not factored form. That means that we can find our leading term and read off our degree and our leading coefficient without having to do anything. For our leading term, we're looking at which term has the highest power of x. That would be this first one. From that, we can read off our leading coefficient. Our leading coefficient is just going to be -1. Our degree is 7. From those two things, we can figure out what our end behavior is. Since our leading coefficient is negative, that means our graph is going to go down on the right. For these, you can write out what the end behavior is in words, or you can draw a picture, either way. So down on the right means it's going to be doing something like that. And then because it's got an odd degree, that means it's going to be doing the opposite thing on the left end. If it's going down on the right, that means it has to be going up on the left. When you get to functions that have as high a degree as this, a lot of times you do get that thing where it looks like a bunch of vertical lines. So it's really kind of hard to tell sometimes from the graph what the end behavior actually is. That's why it's good to be able to do it just on paper. So we'll look at this one and see what it turns out like. The question is, how come this doesn't look like what our picture was here? That's a good possibility that we need to expand our window because we're not seeing the whole graph. The other thing that you need to think about right away also is to make sure that you put your function in here correctly. The leading term is the same thing that I had written down there. That's something I always check first. If this graph doesn't agree with what the end behavior we got on paper was, then we're not seeing the whole graph. There might be another x-intercept that's further over here or something like that. But we don't know without just expanding our window. I'm going to go back to this, and I'm just going to put in some bigger values for my x-min and my x-max, just so that it widens out the window from left to right. I'm just going to put in -50 and +50 and see what that does. So now we can see another whole piece of this graph that we couldn't see before. Before we had that part in the middle that was doing something like this, and now it looks like it's going up here and coming back down over here. Now this does agree with the end behavior that we had over here. It looks like it's going up on the left end over here, and it's coming down on the right end. But without knowing what end behavior to expect, we wouldn't have known whether we were seeing the whole graph or not. We can do the same thing if we have something that's in factored form. Let's look at this one. Now this one, because it's in factored form, we should be able to even get more information about it besides just the end behavior. We should be able to tell what the zeros are and the multiplicities. And those are going to tell us something about what the graph looks like, and we're going to talk about that too. But before we do that, let's just write down those zeros and the multiplicities, and that way we can look at our degree and our leading coefficient. For the zeros, each one of these factors gives us a 0. For this one, because there's an x cubed on the outside of this, that actually counts as a factor. So one of our zeros is going to be 0. We get that from this, and because that x has an exponent of 3, the multiplicity for that one is 3. When we move on to the x minus 2 factor, the 0 that goes with that is 2. That had an exponent of 2, so the multiplicity for that one is 2. And then this one, the 0 would be -1, and the multiplicity would be 1. Now that we've got that, we can add up our multiplicities to get our degree. That means our degree is 6. And if we look at our factored form here, the coefficient that's in front of the whole thing is a 7. So that means our leading coefficient is 7. We can take these two things and think about the end behavior. This time, since our leading coefficient is positive, that means our graph is going to go up on the right. And then since the degree is even, that means it's going to do the same thing on the left end that it does on the right end. So it's also going to go up on the left. This one has kind of the smiley face graph. Now the other thing that we can tell with one like this that's in factored form is we can tell a lot more about what's going on in the middle of the graph, since this just tells us about the two ends. Because we know where our x-intercepts are. And there's one more thing that we can tell about those x-intercepts because we know the multiplicities. With the multiplicities, if the multiplicity is odd, that means that the graph is going to actually cross through the x-axis at that point. For these two, the 0 and the -1, those both have odd multiplicities. The graph is going to cross the x-axis at 0, and it's going to cross the x-axis at x equals -1. That's just because these two are odd. So this is an odd multiplicity, and this is an odd multiplicity. If the multiplicities are even, that's where the graph is just going to come and touch the x-axis and go back. So it's either going to come down, touch the x-axis and go back up, or it's going to come up and touch the x-axis and go back down. So this one in the middle at 2, this has an even multiplicity, so that means we're just going to have a touch there. Let's graph this one and see how that looks. This time we should get everything to agree with what we said. We've got our end behavior. We said it was supposed to be going up on both ends. It looks like we can see it doing that. And then also we've got our zeros. So we had a 0 at 0 and 2 and at -1. We can see all three of those on the graph. At 0 and -1, it was supposed to be actually crossing through the x-axis, so we can see that here and here. And then at 2, it's supposed to be just coming down and touching the x-axis. And this one you can actually kind of see that that's happening. Sometimes it's really hard to tell from your calculator graph if you haven't already figured out on paper where your x-intercepts are. Your calculator graph sometimes can be pretty misleading, because for one like this, it might look like it's only coming down part way and it's not going all the way down to the x-axis. That's why I always have you do this on paper first and then look at your graph, and you should be able to see how your graph matches what you found on paper.